On April 13th, 2029, at exactly 5:46 p.m. Eastern Time, an asteroid the size of the Eiffel Tower will pass between Earth and our communications satellites. It'll be close enough to see with the naked eye, close enough that people in Europe, Africa, and Western Asia will watch a point of light move across the sky faster than any star should move. Close enough that it'll actually be pulled slightly off course by Earth's gravity. The asteroid's name is Apophis, and when astronomers first discovered it in 2004, the calculations were terrifying. There was a 2.7% chance, nearly 1 in 40, that Apophis would hit Earth on that April day in 2029. Those are odds that keep NASA scientists up at night. Further observations ruled out an impact in 2029. We're safe. Apophis will miss us by about 19,000 miles. Close in cosmic terms, but a clean miss. But here's what no one talks about. That close encounter in 2029 is going to change everything. When Apophis passes Earth, our planet's gravity will bend, its orbit. We'll essentially grab this asteroid as it flies by and fling it onto a new trajectory. And we won't know exactly where that trajectory leads until we watch it happen. There's a possibility, small but real, that Earth's gravity will bend Apophis's orbit just right to send it on a collision course with our planet 7 years later. In 2036, or possibly 2068, or according to some newer calculations, 2032. We're talking about a 370-meter wide asteroid, roughly 1,200 feet across, moving at 30,000 miles per hour, with enough kinetic energy to release the equivalent of over 500 megatons of TNT. For context, the largest nuclear weapon ever detonated was 50 megatons. This asteroid would hit with 10 times that force. An impact wouldn't end human civilization, but it would devastate whatever region it struck. If it hit a major city, tens of millions would die. If it hit the ocean, the resulting tsunami could wipe out coastal populations across an entire ocean basin. And the unsettling truth is, we won't know for certain whether it's going to hit us until after the 2029 flyby. Right now, we're watching and waiting, refining our calculations, and preparing for every possible outcome. This is the story of Apophis, the asteroid that might hit Earth, and what it reveals about how prepared we really are for the cosmic shooting gallery we live in. Section 1. The Discovery. Let me take you back to June 19th, 2004. The place is Kitt Peak National Observatory in Arizona. 2 astronomers, Roy Tucker and David Tholen, are conducting a routine survey of the night sky, looking for near-Earth asteroids. Near-Earth asteroids, or NEAs, are space rocks whose orbits bring them close to our planet. Most are harmless. They pass by at safe distances and continue on their way. But every so often, one of these asteroids crosses Earth's orbital path at just the wrong time, and the consequences can be catastrophic. Just ask the dinosaurs. Tucker and Tholen were part of a systematic effort to catalog these objects, to map their orbits and determine which ones might pose a threat. It's tedious work. Most nights, you find nothing interesting. But on this particular night, they spotted something new. A faint point of light moving against the background stars. Too fast to be a distant asteroid in the main belt between Mars and Jupiter. This was something closer, something on an orbit that brought it near Earth. they designated it 2004 MN4, the temporary name given to newly discovered asteroids before they get something more memorable. Over the next few months, astronomers around the world trained their telescopes on 2004 MN4, tracking its position, refining the orbital calculations. And with each new observation, the picture became clearer and more concerning. This asteroid was on an orbit that crossed Earth's path, not just vaguely near it, but directly across it. And the calculations showed that in 2029, it would pass very, very close to our planet. By December 2004, the situation had escalated. When astronomers ran the numbers, accounting for the uncertainties in the measurements, they calculated a 2.7% probability of impact on April 13th, 2029. To put that in perspective, a 2.7% chance means that if you could run the scenario 100 times, the asteroid would hit Earth in about 2 or 3 of those runs. Those are not good odds when the thing you're gambling with is millions of lives. The asteroid briefly reached level 4 on the Torino Scale, a system astronomers use to categorize the threat level of near-Earth objects. Level 4 means a close encounter, meriting attention by astronomers. Current calculations give a 1% or greater chance of collision capable of regional devastation. It was the highest rating ever given to an asteroid, higher than any object before or since. News leaked to the media. Headlines screamed about the potential for catastrophe. NASA held press conferences. The public was, understandably, alarmed. But astronomers kept observing. And this is important. With asteroids, more data almost always reduces the threat level. The uncertainties in our predictions come from limited observations. The more times we see an asteroid, the better we can calculate its orbit, and usually, that better orbit shows the asteroid missing Earth by a comfortable margin. By December 27th, 2004, just a few weeks after the initial alarm, enough observations had been gathered to rule out an impact in 2029. The asteroid would pass close, terrifyingly close, but it would miss. NASA downgraded the threat level to 0. The crisis was over, except it wasn't. Because that close pass in 2029 created a new problem, one that we're still grappling with today. Section 2, the keyhole problem. Here's how gravity works with asteroids. When a massive object like Earth passes near a smaller object like an asteroid, the gravitational interaction can change the asteroid's orbit. This is basic orbital mechanics. The closer the asteroid passes, the more its orbit changes. A distant flyby might barely affect the trajectory, but a close flyby, like the one Apophis will make in 2029, can significantly alter where the asteroid goes next. In 2004, shortly after ruling out the 2029 impact, astronomers started looking at what happens after 2029. If Apophis passes Earth at one distance, it goes on one trajectory. If it passes at a slightly different distance, it goes on a different trajectory. And some of those trajectories lead back to Earth. This is where the concept of a keyhole comes in. Imagine Earth's gravitational field during the 2029 encounter as a kind of cosmic pinball machine. The asteroid is the ball. Depending on exactly where it enters this gravitational field, it'll be deflected in different directions. Most of those directions are safe. They send Apophis on orbits that never threaten Earth again. But there are specific narrow zones called gravitational keyholes, where passing through them would put Apophis on a collision course with Earth on a future orbit. These keyholes are small. We're talking about regions in space only a few hundred meters wide. If Apophis passes through one particular keyhole in 2029, it comes back to hit Earth in 2036. If it passes through a different keyhole, it might hit in 2068. And here's the thing that makes this so nerve-wracking. Before the 2029 encounter, we can't know exactly where Apophis will pass. We know it'll be close, about 19,000 miles from Earth's surface. But our current measurements have uncertainty, maybe a few kilometers of uncertainty in where exactly it'll be during closest approach. That uncertainty is larger than the keyholes. We can't yet say with certainty that Apophis won't pass through one of these dangerous zones. It's like shooting an arrow at a target 100 meters away while wearing blurry glasses. You can see you're aiming near the bullseye, but you can't tell if you're going to hit the exact center or be off by a few inches. Usually, being off by a few inches doesn't matter, but if there's a mine buried at one specific spot on the target, suddenly that precision becomes very important. In 2005 and 2006, astronomers were particularly concerned about a keyhole that would lead to an impact in 2036. At one point, the calculated probability of Apophis threading this needle and hitting Earth in 2036 was about 1 in 45,000. That might sound like long odds, and they are, but for asteroid impacts, that's relatively high. Most asteroids we track have impact probabilities measured in 1 in millions or 1 in billions. Further observations refined the orbit more. By 2013, astronomers were confident that Apophis would not pass through the 2036 keyhole. That particular threat was eliminated, but other potential impacts remained on the table for later dates. 2051, 2060, 2068. The probabilities for these are much lower, currently estimated at less than 1 in 100,000 for 2068, but they're not zero. And here's what keeps astronomers up at night. Those probabilities are based on our current understanding of Apophis's orbit. After the 2029 encounter, when Earth's gravity bends that orbit, we'll essentially be starting over with a new trajectory to calculate. We'll have a much better view of Apophis in 2029. It'll pass close enough for detailed radar observations that will pin down its orbit much more precisely. But until that happens, we're working with uncertainties. And then there's the 2032 scenario. Section 3, the 2032 calculation. In recent years, some orbital dynamics researchers have been running new simulations of Apophis's trajectory, accounting for factors that earlier calculations didn't fully include. Things like the Yarkovsky effect, a subtle but important force where sunlight heats one side of a rotating asteroid, which then radiates that heat away as infrared radiation, creating a tiny thrust that slowly changes the asteroid's orbit over time. And when they run these more sophisticated models, some scenarios show a non-zero probability of impact in 2032, 3 years after the close encounter, not 7. Now, let me be very clear. The official NASA assessment does not list 2032 as a significant threat year. The mainstream scientific consensus focuses on 2068 as the nearest potential impact date with any meaningful, though still very low, probability. But science works through multiple independent calculations. Different researchers using different models and different assumptions sometimes get different results. And a few published papers have suggested that 2032 deserves more attention than it's currently receiving. The probability these studies suggest is still very low. We're talking about something like 1 in 250,000 or less. But it's a non-zero number, and it's closer in time than the 2068 scenario most people focus on. Why would 2032 be a possibility when earlier calculations focused on 2036 and later dates? It has to do with the specific geometry of how Earth's gravity reshapes Apophis's orbit in 2029. Imagine Apophis's orbit as an ellipse, an oval shape. One end of the oval comes very close to Earth's orbit. The other end swings out farther into the solar system. The time it takes for Apophis to complete one orbit, to go around the sun and come back, is its orbital period. When Earth's gravity tugs on Apophis in 2029, it can stretch or compress this ellipse, changing how long it takes to complete an orbit. If the period gets shortened just right, Apophis might come back to cross Earth's orbit exactly when Earth is also at that same point. The 2029 encounter could potentially adjust Apophis's orbital period to bring it back in resonance with Earth's orbit in 2032. It's a complex interaction that depends on thousands of factors, including the exact trajectory through Earth's gravitational field, the asteroid's rotation rate, its density distribution, and the Yarkovsky effect during the years between encounters. Most of these factors are still not precisely known. We have estimates, but estimates come with uncertainties, and those uncertainties propagate forward in time, creating a range of possible future positions for Apophis. In most of that range, Apophis misses Earth by a wide margin, but in some scenarios, rare, low probability scenarios, it doesn't. This is why we keep watching. This is why observatories around the world continue to track Apophis every time it comes into view. Every new observation reduces the uncertainty a little more, narrows the range of possible futures, and hopefully confirms what we expect: that Apophis will miss us. But until we get through the 2029 encounter and see exactly where Earth's gravity sends this asteroid, we can't be completely certain. Section 4. What we know about Apophis. Let's talk about the asteroid itself. What is Apophis? Where did it come from? What's it made of? Apophis is what astronomers call an Aten-class asteroid. This means its orbit brings it inside Earth's orbit as it goes around the sun. Most of the time, it's actually closer to the sun than we are. Its orbit is elliptical, taking it from about 0.75 astronomical units from the sun at its closest. AU stands for astronomical unit, the distance from Earth to the sun, to about 1.1 AU at its farthest. Earth, for reference, orbits at 1 astronomical unit. The asteroid completes one orbit around the sun every 323.6 days, a bit less than an Earth year. This means that over time, it cycles through different positions relative to Earth's orbit, sometimes crossing our path, sometimes not. Apophis is roughly 370 meters across at its widest point, about 1,214 feet. To give you a sense of scale, that's about as tall as the Empire State Building is high. Or if you're more familiar with Paris, it's about the same size as the Eiffel Tower. The shape appears to be somewhat irregular, not a perfect sphere, but more of an elongated potato-like shape. This is typical for asteroids. Only very large asteroids have enough self-gravity to pull themselves into spheres. Smaller ones like Apophis are just whatever shape they happened to form with, usually the result of countless collisions over billions of years. Its composition is what we call SQ type, based on spectroscopic observations. That's fancy astronomy speak, for we looked at the sunlight reflecting off it and analyzed the colors. SQ-type asteroids are stony, mostly made of silicate minerals similar to the rocks you'd find on Earth. Not metal, not ice, but rock. The surface is probably covered in regolith, a layer of dust and small rocks created by billions of years of micrometeorite impacts. If you could stand on Apophis, it would look like a gray, dusty, cratered landscape, not unlike the Moon, but on a much smaller scale. Gravity on Apophis would be almost imperceptible. The surface gravity is estimated to be about 0.000026 times Earth's gravity, meaning you'd weigh about 260,000 times less than you do on Earth. If you weigh 150 pounds on Earth, you'd weigh about 0.0006 pounds on Apophis. You could literally jump off the asteroid and escape into space if you pushed off with even moderate force. Walking would be impossible. Every step would launch you into a ballistic trajectory. If you somehow landed on Apophis, you'd need to anchor yourself to the surface or risk floating away. The asteroid rotates once every 30.4 hours, so a day on Apophis lasts about 30 Earth hours. This relatively slow rotation means the Yarkovsky effect is significant. The sun heats one side during its long day, and that side radiates heat for hours as the asteroid rotates, creating a tiny but persistent push that changes its orbit over years and decades. We believe Apophis is a fragment of a larger asteroid that broke apart at some point in the past, probably from a collision in the asteroid belt. Most near-Earth asteroids have this origin story. They're pieces of larger bodies that were shattered by impacts and then had their orbits perturbed by gravitational interactions with planets until they ended up in Earth-crossing orbits. The asteroid is probably between 100 million and 1 billion years old in its current form, though the material it's made of is as old as the solar system itself, about 4.6 billion years. And here's something interesting. Apophis isn't alone. It might have a small companion, a tiny moonlet orbiting it, or perhaps it's a binary system, two asteroids orbiting each other. Observations in 2021 suggested this possibility, though it's not yet confirmed. If true, this would complicate deflection efforts if we ever needed to try pushing Apophis off a collision course. One more crucial detail. We now know Apophis is about 3 times more massive than we initially thought. Earlier estimates put its mass at about 27 million tons. Newer radar observations, particularly from the Arecibo Observatory before it collapsed in 2020, suggested the mass is closer to 61 million tons. Why does this matter? Because mass determines how hard it would be to deflect the asteroid. A 61 million ton object requires a lot more force to change its trajectory than a 27 million ton object. If we ever do need to deflect Apophis, knowing its true mass is critical for planning the mission. Section 5, what an impact would look like. Let's talk about what would actually happen if Apophis hit Earth, because the details matter. This isn't an extinction-level event like the asteroid that killed the dinosaurs, but it's not trivial either. The asteroid that ended the Cretaceous period 66 million years ago was about 10 kilometers across, roughly 30 times wider than Apophis. It struck with enough force to vaporize rock, create wildfires across continents, and throw so much dust into the atmosphere that sunlight was blocked for years. That's what an extinction-level impact looks like. Apophis is much smaller, but smaller than extinction level still leaves a lot of room for catastrophe. Let's run through the scenario. Apophis is approaching Earth at about 12.6 kilometers per second, roughly 28,000 miles per hour. At that speed, it would cross the United States from coast to coast in about 4 minutes. The asteroid enters Earth's atmosphere. For context, the space shuttle re-entered at about 8 kilometers per second, and the heat and friction of re-entry at that speed was intense enough to require specialized heat shields. Apophis is coming in faster and is vastly more massive. At these speeds, the asteroid doesn't slow down significantly in the atmosphere. For smaller meteors, atmospheric friction causes them to slow down, heat up, and break apart. That's why we see shooting stars. But Apophis is too big and too fast. The atmosphere is like tissue paper to it. The passage through the atmosphere takes only a few seconds. People on the ground wouldn't even see it coming unless they happen to be looking in exactly the right direction. And even then, it would just be a bright flash across the sky, there and gone almost before the brain could register what it saw. Then impact. If it hits land, the asteroid strikes the surface with a kinetic energy equivalent to about 510 megatons of TNT. For comparison, the Hiroshima atomic bomb was about 0.015 megatons. The largest nuclear weapon ever tested, Tsar Bomba, was 50 megatons. Apophis would hit with about 10 times the force of Tsar Bomba. At the impact site, everything within several kilometers is simply obliterated, vaporized. The asteroid itself is partially vaporized by the impact. Rock at the impact point is instantly heated to temperatures exceeding the surface of the sun. A fireball expands outward at supersonic speeds. A crater forms, probably about 3 to 5 kilometers across and 600 to 800 meters deep. For context, that's about the size of Meteor Crater in Arizona, except formed in seconds rather than thousands of years. The shock wave from the impact radiates outward. Within 20 kilometers of ground zero, the overpressure would be strong enough to collapse most buildings and kill anyone not in underground shelters. The blast wave would be comparable to the pressure wave from a nearby nuclear detonation. Out to about 60 kilometers, windows would shatter, buildings would be damaged, injuries would be widespread. The shock wave would be felt hundreds of kilometers away, like a major earthquake. Debris ejected from the crater would rain down across hundreds of square kilometers. Some of this debris would be thrown high enough and fast enough to reach space, only to fall back to Earth as secondary impacts scattered across a wide area. If the impact occurred in a populated area, a major city, the death toll would be measured in millions. Not from the direct impact. Most cities are larger than the immediate devastation zone, but from the blast wave, debris, fires, and secondary effects. If it hits the ocean, which is statistically more likely since oceans cover 71% of Earth's surface, the scenario is different but no less catastrophic. The asteroid would punch through several kilometers of ocean and hit the seafloor, creating an underwater crater and vaporizing enormous quantities of water. The energy would generate a tsunami. Not just a tsunami, but a mega tsunami. Waves radiating out from the impact could be 20 to 30 meters high, 60 to 100 feet, when they reach coastlines hundreds or thousands of kilometers away. These waves would travel at speeds of 800 kilometers per hour in deep water, slowing only as they approach shore, where they would rise up and surge inland. Coastal cities across an entire ocean basin could be devastated. If Apophis hit in the middle of the Atlantic, for instance, waves could strike the eastern seaboard of North America, the Caribbean, and the western coasts of Europe and Africa. The death toll from an ocean impact could actually be higher than a land impact because of the number of people living in coastal areas. Beyond the immediate impact zone, there would be global effects, though not as severe as with larger asteroids. The dust and debris thrown into the atmosphere might cause temporary climate cooling, a mini-impact winter lasting a few years. Sunlight would be reduced, affecting agriculture in some regions. The economic impact would be staggering. We're talking trillions of dollars in damage, potentially triggering a global recession or even depression, depending on what was hit. This is not an extinction event. Humanity would survive. Civilization would continue. But it would be one of the worst disasters in recorded history, comparable to or exceeding the worst natural disasters we've experienced. And here's the thing that makes Apophis particularly concerning. It's big enough to cause this kind of catastrophe, but small enough that we only discovered it in 2004. There might be other Apophis-sized asteroids out there that we haven't found yet. The odds that Apophis specifically will hit us are low, but the odds that something like Apophis will hit Earth eventually, those approach certainty over long enough timescales. Section 6. The history of close calls. Apophis isn't the first asteroid to give us a scare. Let me give you some perspective on how often this happens and how lucky we've been. On March 23rd, 1989, an asteroid designated 4,581 Asclepius passed within 700,000 kilometers of Earth, about twice the distance to the Moon. That might sound like a comfortable margin, but in astronomical terms, it's a near miss. We didn't detect Asclepius until after it had already passed. If it had hit Earth, it would have released energy equivalent to about 1,000 megatons, twice what Apophis would release. On March 18th, 2004, just a few months before Apophis was discovered, a 30-meter asteroid called 2004 FH passed within 43,000 kilometers of Earth, about 1/10 the distance to the Moon. It's one of the closest approaches ever recorded. An asteroid that size wouldn't cause global catastrophe, but if it had hit a city, the results would have been devastating. In 2009, astronomers discovered an asteroid called 2009 DD45, 3 days after it had already passed Earth at a distance of 72,000 kilometers. It was about 30 meters across, similar in size to the object that exploded over Chelyabinsk, Russia in 2013. Speaking of Chelyabinsk, on February 15th, 2013, A roughly 20-meter asteroid entered Earth's atmosphere over Russia, traveling at 19 kilometers per second. It exploded about 30 kilometers above the ground, with energy equivalent to about 500 kilotons of TNT, roughly 30 times the Hiroshima bomb. The shockwave shattered windows across a wide area, injuring about 1,500 people, mostly from flying glass. It was the largest object to enter Earth's atmosphere since the Tunguska event in 1908. And here's the scary part. We never saw it coming. The asteroid approached from the direction of the sun, where our telescopes can't look, because, looking directly at the sun is bad for both telescopes and eyes. We had no warning. The first we knew about it was when it exploded over a populated area. Tunguska, by the way, was likely caused by an asteroid or comet about 60 to 190 meters across that exploded in the air over Siberia in 1908. The explosion was equivalent to about 10 to 15 megatons and flattened an estimated 80 million trees over 2,150 square kilometers. If it had hit a few hours earlier or later, when Earth's rotation had placed a major city under that point in its trajectory, millions would have died. These aren't ancient history. These are modern events, happening in our lifetimes or our grandparents' lifetimes. The statistical reality is that Earth is hit by asteroids on a regular basis. Objects less than 1 meter across. Multiple times per day, they burn up harmlessly. Objects 1 to 10 meters across, several times per year, usually explode in the atmosphere. Objects 10 to 100 meters across, Tunguska size. Every few centuries to millennia. Objects 100 meters to 1 kilometer across, Apophis size. Every few 100,000 years. Objects larger than 1 kilometer across. Every few million years. Objects 10 plus kilometers across, dinosaur killer size. Every 100 plus million years. These are statistical averages. The actual timing is random. We could go millions of years without a large impact, or we could get hit tomorrow. Probability doesn't care about fairness or timing. What's changed in recent decades is that we've started actually looking for these objects. Before the 1990s, we had cataloged only a handful of near-Earth asteroids. We knew they existed, but we weren't systematically searching for them. The 1989 Asclepius near miss was a wake-up call. Congress directed NASA to find and catalog at least 90% of near-Earth asteroids larger than 1 kilometer. Later, the threshold was lowered to 140 meters, objects large enough to cause regional devastation. As of 2024, we've found over 30,000 near-Earth asteroids. Of those, about 2,300 are classified as potentially hazardous, meaning they're large enough to cause significant damage, and their orbits bring them close enough to Earth that they deserve monitoring. Apophis is one of those 2,300. It's not unique in being potentially hazardous. What makes it special is how close it's going to pass in 2029 and the uncertainty about what happens after. But here's the reassuring part. Of the approximately 2,300 potentially hazardous asteroids we've found, we don't expect any of them to hit Earth in the next 100 years. Apophis has the highest combined probability of any known asteroid, and even its probability is very low, less than 1 in 100,000 for the 2068 encounter, and even lower for 2032. The real concern isn't the asteroids we've found and are tracking. It's the ones we haven't found yet. Section 7. The detection gap. Here's something that should keep you up at night. We've found most of the really big asteroids, the ones that could cause mass extinctions. NASA estimates we've cataloged about 95% of near-Earth asteroids larger than 1 kilometer. But when you get down to Apophis-sized objects, 300 to 500 meters across, we've probably only found about 40% of them. That means there are potentially hundreds or thousands of Apophis-sized asteroids out there that we don't know about. And for objects in the 100 to 300 meter range, still large enough to cause devastating regional destruction, we've probably found less than 30%. Why haven't we found them all? Several reasons. They're small and dark. Asteroids don't emit light. They only reflect sunlight. A 300-meter asteroid at the distance of the Moon reflects about as much light as a 15th magnitude star. That's too faint to see with the naked eye or even with binoculars. You need a decent telescope, and you need to know where to look. Space is really, really big. Even within Earth's orbital neighborhood, there's a lot of volume to search. Asteroids can be anywhere in that space, and they're moving, so you need to systematically survey the entire sky repeatedly to catch objects as they pass through your field of view. Some asteroids approach from the direction of the sun. Our telescopes can't look toward the sun without being blinded by its light. This creates a cone of space we can't observe. If an asteroid's orbit brings it toward Earth from that direction, like the Chelyabinsk meteor did, we won't see it until it's already passed by or hit us. Dark asteroids are harder to spot. Some asteroids are made of very dark material that reflects only 5% or less of the sunlight hitting them. These are much harder to detect than brighter, more reflective asteroids. Apophis is relatively dark, which is one reason it wasn't discovered until it had already passed relatively close to Earth. Limited telescope time. There are only so many telescopes dedicated to asteroid hunting, and they can only observe when the sky is dark and clear. Cloudy nights, full moon, periods, and equipment malfunctions all reduce observing time. Many near-Earth asteroid surveys are done by relatively small telescopes because the big professional telescopes are in high demand for other science. The good news is that detection is improving. New telescopes are coming online, including space-based systems that can observe from angles not possible from Earth's surface. The Vera C. Rubin Observatory in Chile, expected to begin full operations soon, will be able to survey the entire visible sky every few nights with unprecedented sensitivity. It should dramatically increase our discovery rate of near-Earth asteroids. NASA's NEO Surveyor mission, planned for launch in 2026, will be a space telescope specifically designed to find and track near-Earth asteroids, including those that approach from the direction of the sun. But even with these improvements, we're not going to find everything immediately. It'll take years or decades to build up a comprehensive catalog. And there will always be some objects we miss until it's too late. The terrifying possibility is that there's an object out there right now, unknown and uncatalogued, on a collision course with Earth in the next few decades. We wouldn't know about it until someone happens to spot it, and depending on when that discovery occurs, we might not have enough time to do anything about it. This is why astronomers keep searching, keep watching, keep refining their catalogs. Every new discovery is one more object we can track, one more potential threat we can assess and prepare for. Section 8. The 2029 Flyby. What to expect? Let's talk about what's actually going to happen in 2029, because the close encounter itself will be a remarkable event from both scientific and public perspectives. On Friday, April 13th, 2029. Yes, Friday the 13th, because the universe has a sense of dramatic irony. Apophis will pass within 31,600 kilometers of Earth's center. Subtract Earth's radius of about 6,400 kilometers, and you get a closest approach of about 19,000 miles from the surface. To put that in context, the Moon orbits at about 384,000 kilometers from Earth. GPS satellites orbit at about 20,000 kilometers. Geostationary communications satellites orbit at about 35,800 kilometers. Apophis will pass between Earth's surface and the ring of geostationary satellites. It will literally fly through our satellite belt. The close approach will occur at approximately 5:46 p.m. Eastern Daylight Time. The exact time and location of closest approach will be refined as we get closer to 2029, but current calculations show it passing over the Atlantic Ocean, visible from Europe, Africa, and Western Asia. For people in the visibility zone, this will be a naked eye event. Apophis will appear as a point of light moving across the sky, taking several hours to cross from horizon to horizon. It won't look like a typical star or planet. It will be moving noticeably, tracking across the sky at a rate visible to the naked eye. At its brightest, Apophis should reach about magnitude 3.3, easily visible from dark locations, though you might have trouble seeing it from light-polluted cities. For comparison, the faintest stars you can typically see with the naked eye in a dark location are about magnitude 6. With binoculars or a small telescope, Apophis will be a spectacular sight. You'll see it moving in real time, its motion obvious over minutes rather than hours. Amateur astronomers will be tracking it across the sky, photographing it, measuring its position. But the real science will be happening at professional observatories and with radar facilities. The 2029 flyby will give us the best opportunity we've ever had to study an asteroid this size at close range without sending a spacecraft to it. Radar observations will be able to map Apophis's surface in incredible detail. The Goldstone and Arecibo radio telescopes, if they're operational. Arecibo collapsed in 2020, and its future is uncertain, can achieve resolutions of a few meters when an asteroid is this close. We'll be able to see boulders on the surface, measure the asteroid's exact size and shape, study its rotation, and even look for moons or satellites. Optical telescopes will observe how Apophis reflects light, giving us information about its surface composition. Is it covered in fresh, bright regolith or old, dark, weathered material? Are there any signs of recent impacts or geological activity? And we'll be able to measure Apophis's orbit with unprecedented precision. The positional measurements during the 2029 flyby will reduce the uncertainty in the orbital calculation by several orders of magnitude. This is crucial because it will tell us whether Apophis will pass through any of the gravitational keyholes that could lead to future impacts. After April 13th, 2029, we'll have a much clearer picture of whether Apophis poses any threat to Earth in 2036, 2051, 2068, or any other future date. The flyby will also test our detection and tracking capabilities. This is essentially a dress rehearsal for the day when we detect an asteroid that's actually on a collision course. How well can our global network of telescopes track a fast-moving object? How quickly can we gather and analyze the data? How effective is our international coordination? NASA, ESA, European Space Agency, and other space agencies are already planning observation campaigns for the 2029 event. They'll be coordinating telescope time, scheduling radar observations, and possibly even sending spacecraft to rendezvous with Apophis during the flyby. One proposal is to have a small spacecraft already in orbit around or near Apophis during the Earth encounter, using the spacecraft's instruments to measure how Earth's gravity affects the asteroid. This would give us incredibly valuable data about asteroid orbits and gravitational interactions. From a public perspective, the 2029 flyby will be a global event. News media will be covering it extensively. There will almost certainly be misinformation and panic-mongering from some sources, claiming that the asteroid might still hit us, or that the government is hiding the true danger. This is why public education about Apophis is important now, well before the event. People need to understand what's actually happening, what the risks are, minimal, and what to expect. The 2029 flyby is not dangerous. It's a scientific opportunity, but it's also a reminder. A 370-meter asteroid passing closer than our satellites is a demonstration of how close we live to potential catastrophe. We exist in a cosmic shooting gallery, and every so often, a bullet passes close enough for us to hear the whistle. Section 9. How we calculate asteroid orbits. Let me explain how we actually figure out where an asteroid is going to be years or decades in the future, because understanding this helps you appreciate both the precision and the limitations of our predictions. When an astronomer discovers an asteroid, they record its position in the sky and the exact time of the observation. One observation tells you almost nothing. You know the asteroid is somewhere along the line of sight from Earth in that direction, but you don't know how far away it is or how fast it's moving. Two observations, taken hours or days apart, give you a direction of motion. You can see that the asteroid has moved from position A to position B, so you know roughly which way it's traveling across the sky. 3 observations, especially if they span several days or weeks, let you start calculating an orbit. You can use Newton's laws of motion and gravity to work backward from those 3 positions to figure out an elliptical orbit that would cause the asteroid to be in those 3 places at those 3 times. But 3 observations don't give you a precise orbit. There's still a lot of uncertainty. The asteroid could be on a variety of different orbits that would all look similar, given just 3 data points. As you add more observations, 10, 20, 100, the uncertainty shrinks. You're constraining the possible orbits more and more tightly. Eventually, you get to a point where you can predict the asteroid's position years into the future, with reasonable accuracy. But reasonable accuracy is relative. Even with thousands of observations, there's still some uncertainty in the orbital calculation. This comes from several sources. Measurement uncertainty. Telescopes can only measure positions to within a certain precision. Even the best observations have errors of a fraction of an arcsecond. An arcsecond is 1/36th of a degree. When you're observing an asteroid millions of kilometers away, that tiny angular uncertainty translates to thousands of kilometers of position uncertainty. Perturbations. An asteroid's orbit isn't just determined by the sun's gravity. The planets also pull on it, slightly altering its trajectory. For near-Earth asteroids, Earth's gravity is a significant perturbation, as is the gravity of Venus, Mars, and Jupiter. Calculating all these gravitational effects requires knowing the exact positions of all the planets, which we know very well, but not perfectly. Non-gravitational forces. Things like the Yarkovsky effect, the tiny thrust from the asteroid radiating absorbed sunlight, and solar radiation pressure, photons from the sun physically pushing on the asteroid, create small but accumulating changes to the orbit. These effects depend on the asteroid's size, shape, rotation, surface properties, and composition, things we often don't know precisely. Relativity. At the level of precision we're working with, even general relativistic effects matter. Einstein's theory of relativity predicts that orbits behave slightly differently than Newton's laws would suggest, especially when objects are close to the sun. These relativistic corrections are small but measurable and need to be included in accurate orbital calculations. All of these factors create uncertainty that grows over time. An orbital calculation might predict an asteroid's position 10 years from now to within a few hundred kilometers. But 50 years from now, the uncertainty might grow to tens of thousands of kilometers. And 100 years from now, it could be hundreds of thousands of kilometers or more. This is why near-term predictions are much more reliable than far future predictions. It's also why close encounters with planets are so problematic. They introduce huge changes to the orbit that are very sensitive to tiny uncertainties in the approach geometry. For Apophis, our current observations let us predict its position in 2029 quite well, probably to within a few kilometers. But after the 2029 Earth encounter, the uncertainty explodes because small differences in exactly where Apophis passes relative to Earth will produce large differences in its post-encounter orbit. Think of it like a pool game. If you hit a ball exactly right, you can predict where it'll go. But if your aim is off by just a tiny fraction of a degree, the ball might hit the cushion at a slightly different angle and end up somewhere completely different. The 2029 encounter is like Apophis bouncing off Earth's gravity well. Tiny uncertainties in the approach translate to large uncertainties in the departure trajectory. This is why we need to observe the 2029 flyby so carefully. Those observations will tell us exactly where Apophis goes afterward, allowing us to recalculate the orbit with much better precision and determine whether any future encounters pose a real threat. Section 10. The deflection question. Here's the question everyone wants answered. If we determined that Apophis was actually going to hit Earth, could we stop it? The short answer is, probably, if we had enough warning time. The longer answer is complicated. because asteroid deflection is hard, and we've never actually done it on an asteroid that poses a real threat. In September 2022, NASA successfully completed the DART Double Asteroid Redirection Test mission. A spacecraft intentionally crashed into Dimorphos, a small moon orbiting the asteroid Didymos, at 6.6 kilometers per second. The impact successfully changed Dimorphos' orbital period by 33 minutes. Proof of concept that we can alter an asteroid's trajectory with a kinetic impactor. But Dimorphos is about 160 meters across, less than half the size of Apophis. And more importantly, we didn't need to move it very much. We were just testing the technology, not preventing an actual impact. Deflecting Apophis would be a much bigger challenge. Here are the main options we'd have. Kinetic impactor. This is the DART approach. Slam a spacecraft into the asteroid at high speed. The impact transfers momentum, giving the asteroid a slight push. Do this far enough in advance of a predicted impact, and that small push accumulates over time into a significant change in position. For Apophis, you'd probably need multiple kinetic impactors, not just one. The asteroid is massive, 61 million tons, and moving it enough to turn a hit into a miss would require substantial momentum transfer. The advantage of kinetic impactors is that we already have the technology. We can build and launch them with current spacecraft. The disadvantage is that they're inefficient. Most of the impactor's momentum is wasted in creating a crater, with only a fraction going into moving the asteroid. Gravity tractor. This is a more elegant but slower method. You park a spacecraft near the asteroid and use the gravitational attraction between the spacecraft and the asteroid to slowly pull the asteroid onto a different trajectory. The advantage is precision. You can carefully control exactly how much you're moving the asteroid and in what direction. The disadvantage is that gravitational forces are weak, so this method only works if you have years or decades of warning time. For Apophis, a gravity tractor mission would probably need at least 5 to 10 years to produce enough deflection. It's not an option if we only have a few years' warning. Nuclear device. This is the Hollywood option, but not in the way movies portray it. You don't want to blow up the asteroid. That just turns one big problem into many smaller problems, and some of those fragments might still hit Earth. Instead, you'd detonate a nuclear device near the asteroid, not on it. The energy from the detonation would vaporize material from the asteroid's surface, and the rapidly expanding vapor would act like a rocket engine, pushing the asteroid in the opposite direction. This is actually one of the most efficient methods in terms of deflection per unit mass of equipment sent to the asteroid. A single large nuclear device could potentially deflect Apophis enough to prevent an impact if deployed several years in advance. The disadvantages are political and practical. Using nuclear weapons in space is controversial and regulated by international treaty, and you'd need to design a specialized device and delivery system for this specific purpose. We don't have one ready to go. Mass driver/ion beam. Over long timescales, you could mine material from the asteroid and eject it in one direction using the reaction force to push the asteroid the other way, or use an ion beam from a spacecraft to vaporize and eject surface material. These methods are efficient and controllable, but very slow. They only work with decades of warning time. The critical factor in all of these methods is warning time. If we detected Apophis was on a collision course 20 years before impact, we'd have excellent chances of deflecting it successfully with almost any of these methods. If we only had 5 years warning, our options narrow. We'd probably need to use kinetic impactors or nuclear devices, and we'd need to act quickly. If we only had 1 to 2 years warning, perhaps because the 2029 encounter put Apophis on an unexpected collision course and we didn't calculate it in time, our options become very limited and the probability of success drops significantly. This is why continuous observation and early detection are so critical. The earlier we know about a potential impact, the more options we have and the higher our chances of success. For Apophis specifically, if the 2029 flyby somehow showed that impact was likely in 2032, giving us less than 3 years warning, we'd be in a very difficult situation. We could probably launch a deflection mission in that time frame, but it would be rushed, risky, and might not be effective enough. If impact wasn't until 2036 or later, we'd have much better chances. 7 or more years gives us time to design, build, and deploy a proper deflection mission with backup options if the first attempt doesn't work as planned. The good news is that the most likely outcome is that we won't need to deflect Apophis at all. But the planning is important because Apophis won't be the last asteroid to threaten Earth. The techniques we develop and test for Apophis will be used on future asteroids that do pose real threats. This asteroid might hit Earth in 2032. YouTube script, Part 2, Section 11, the International Coordination Challenge. Here's something that doesn't get talked about enough. Asteroid defense isn't just a technical problem, it's also a political and organizational one. Let's say we determine that Apophis is on a collision course with Earth. Who decides what to do? Who launches the deflection mission? Who pays for it? And most importantly, who takes responsibility if something goes wrong? These aren't trivial questions. An asteroid deflection mission could cost billions of dollars and take years to plan and execute. That kind of commitment requires international cooperation on a scale we've rarely achieved. Currently, there's no single international body with the authority and resources to organize a planetary defense mission. Instead, we have a patchwork of organizations. NASA's Planetary Defense Coordination Office is the primary U.S. agency responsible for detecting and tracking near-Earth objects and planning potential deflection missions. They have the most resources and the most developed plans, but they're a U.S. government agency, not an international one. The European Space Agency has its own Planetary Defense Office and has conducted studies on asteroid deflection missions. The ESA's Hera mission, launched to study the results of the DART impact, demonstrates their commitment to planetary defense research. The United Nations Office for Outer Space Affairs has established the International Asteroid Warning Network, IAWN, and the Space Mission Planning Advisory Group, SMPAG. These are coordination bodies meant to facilitate information sharing and joint planning among member nations. Individual nations like Russia, China, Japan, and India have their own space programs and could potentially contribute to a deflection mission. But international politics makes coordination complicated. In an ideal world, we'd have a well-funded, internationally supported organization with pre-approved protocols for asteroid deflection. When an impact threat was identified, this organization would immediately spring into action, launching a deflection mission using pre-designed spacecraft and equipment. In reality, we'd probably have months of meetings, debates about who should lead the mission, arguments about how to share costs, and political maneuvering before anything got launched. This problem gets even more complicated when you consider the target location. An asteroid doesn't threaten Earth in general. It threatens specific regions based on where and when it impacts. Let's say our calculations show that Apophis will hit somewhere in the Atlantic Ocean on a specific date and time. That's a huge area, but we can narrow it down to a ground track, a line across the Earth's surface representing the possible impact locations. Different points on this ground track might be more or less populated. The asteroid might hit in the middle of the ocean, or it might hit closer to the coast of North America, Europe, or Africa. The people in different regions would have very different levels of risk. Now imagine you could deflect the asteroid, but the deflection might change which region gets hit. Maybe the original trajectory would hit the Atlantic, but the deflection attempt would send it toward the Pacific instead. Have you solved the problem or just moved it? Some regions might actually want the deflection to happen, while others might oppose it because it increases their risk. This creates an impossible political situation where there's no course of action that makes everyone safer. There's also the question of who bears liability if a deflection attempt goes wrong. Let's say the US launches a kinetic impactor to deflect Apophis, but the impact is slightly off target, and instead of deflecting the asteroid away from Earth, it deflects it onto a collision course when it would have missed otherwise. Who's responsible for that? Who pays the damages? What if the botched deflection causes the asteroid to hit a different country than the one it would have hit originally? These aren't hypothetical concerns. They're real issues that need to be addressed in international treaties and agreements before we're faced with an actual deflection scenario. The good news is that progress is being made. The Outer Space Treaty of 1967 provides some framework, though it was written long before asteroid deflection was a practical concern. More recent discussions at the UN have started addressing these issues more directly. But we're not there yet. We don't have a clear, universally accepted protocol for who decides, who acts, and who's responsible. And if Apophis or another asteroid does threaten Earth in the near future, we'll be making up the governance structure on the fly while also trying to solve the technical problem of deflection. This is why experts in planetary defense keep emphasizing that we need to solve the political and organizational challenges now, before we're in a crisis. We need treaties, agreements, decision-making frameworks, and pre-positioned resources so that when the day comes, we can act quickly and decisively. Section 12, the economic cost of uncertainty. Let's talk about money for a minute, because asteroid threats have economic implications even when the probability of impact is very low. Apophis, with its current impact probability of less than 1 in 100,000 for 2068, doesn't warrant massive spending on deflection preparations. The expected value of the threat, the probability of impact multiplied by the cost of an impact, is relatively low compared to other risks we face. But uncertainty itself has a cost. Insurance companies, for instance, have to account for asteroid risk in their long-term planning. A 1 in 100,000 chance of a catastrophic impact that could cause hundreds of billions or even trillions of dollars in damage is a non-trivial risk when you're running actuarial calculations. Coastal property values could theoretically be affected if an ocean impact was considered likely. Why invest in beachfront real estate if there's a meaningful chance of a mega tsunami in the next few decades? Satellite operators have to consider the risk of Apophis passing through the satellite belt in 2029. While the chance of an actual collision between Apophis and a specific satellite is astronomically small, space is big, satellites are small, the close pass does create some non-zero risk. More broadly, the existence of undetected asteroids creates a constant background risk that affects how we think about long-term planning. Why invest in 50-year infrastructure projects if there's a chance an asteroid could destroy them before they pay off? Now, in practice, these concerns are mostly theoretical. Asteroid risk is so small compared to other risks, climate change, war, economic recession, pandemics, that it doesn't significantly influence most decision-making. But it does affect government budgets for space programs. Every dollar spent on asteroid detection and tracking is a dollar that could be spent on other priorities. The political question is, how much should we spend on preparing for a low probability but high consequence event? Different countries answer this differently. The United States currently spends about $150 million per year on planetary defense, asteroid detection, tracking, and deflection research. That's less than 1% of NASA's budget and a tiny fraction of the overall federal budget. Is that enough? Too much? It's hard to say. We've never experienced a catastrophic asteroid impact in modern history, so we don't have good intuition for how much we should spend to prevent one. Economists have tried to calculate optimal spending based on probability and consequence, and most suggest current spending is about right or slightly low. But these calculations are highly uncertain because we don't know the true probability of impact. We only know about the asteroids we've found, not the ones we haven't. There's also the question of opportunity cost. Every dollar spent on planetary defense is a dollar not spent on other space science, earth science, or social programs. In a world of limited budgets, choices have to be made. But here's the thing. Asteroid defense is one of those rare problems where a relatively small investment can potentially save millions or even billions of lives. Unlike many challenges where throwing money at the problem shows diminishing returns, planetary defense is highly scalable. More money means more telescopes, more survey time, faster detection of threats, and better funded deflection technology development. The relationship between investment and safety is fairly linear up to a point. And unlike some risks we spend money preparing for, asteroid impacts are preventable. We can't stop earthquakes or hurricanes, only mitigate their damage. But with enough warning and the right technology, we can stop asteroid impacts completely. From that perspective, spending even a few $1 billion per year on planetary defense seems like a bargain. It's cheap insurance against a potentially catastrophic event. The challenge is that the political system doesn't reward preparation for events that don't happen. If we spend money on asteroid defense and no asteroid hits us, politicians don't get credit for averting a disaster. They get criticized for wasting money on a threat that never materialized. Only if an asteroid actually threatens Earth and we successfully deflect it would the value of planetary defense spending be obvious to everyone. This creates a perverse incentive structure where we're likely to underfund planetary defense until we actually need it, at which point it might be too late to respond effectively. Apophis, in this context, is actually valuable even though it probably won't hit us. It keeps planetary defense in the public and political consciousness. It justifies continued investment in detection and deflection technology. It serves as a reminder that asteroid impacts aren't just ancient history or science fiction. They're real, ongoing risks that we need to prepare for. Section 13. The naming of Apophis. Let's take a brief detour to talk about why this asteroid is called Apophis, because the name itself is interesting and kind of fitting in a dark way. When asteroids are first discovered, they're given temporary designations based on the date of discovery. Apophis was initially called 2004 MN4, discovered in 2004 in the second half of June M, and it was the 100th asteroid discovered in that half-month period, N4. After the orbit is confirmed and the asteroid is officially catalogued, the discoverers get to propose a permanent name. For near-Earth asteroids, there's a tradition of using mythological names from various cultures. Roy Tucker, one of the co-discoverers, suggested the name Apophis. In ancient Egyptian mythology, Apophis, also spelled Apep, was a serpent deity who embodied chaos and destruction. He was the enemy of Ra, the sun god, and was believed to attack Ra's solar barge every night as it traveled through the underworld. Every night, according to the myth, the gods would have to fight off Apophis to protect Ra and ensure the sun would rise again. If Apophis ever succeeded in defeating Ra, it would bring about the end of the world. So they named an asteroid that could potentially bring catastrophe to Earth after a deity of chaos and destruction who threatens the world every night. It's appropriate in a grimly poetic way. The name was officially approved by the International Astronomical Union in 2005, and it's stuck ever since. There's also a cultural connection that makes the name even more fitting. The asteroid was discovered at Kitt Peak Observatory in Arizona, and there's a connection to the TV show Stargate SG-1, which featured a villain named Apophis. The show used Egyptian mythology heavily. One of the discoverers was a fan of the show, and that influenced the naming choice. So this asteroid threatening Earth is named after a chaos serpent that tries to end the world every night, with a nod to science fiction. It's the kind of synchronicity that feels almost too perfect. Other near-Earth asteroids have similarly evocative names. Icarus, who flew too close to the sun; Phaethon, who lost control of the sun's chariot and nearly destroyed the Earth; and Bennu, an Egyptian deity associated with death and rebirth. Astronomers clearly have a sense of dramatic irony when naming objects that could potentially cause global catastrophes. But beyond the mythology, the name serves a practical purpose. It's memorable and distinctive. When you're tracking thousands of asteroids, having a name that sticks in people's minds is valuable. Apophis is much easier to remember and talk about than asteroid 99,942, its official number, or 2004 MN4. and the name has entered popular culture. Apophis is probably the most famous asteroid among the general public, besides the one that killed the dinosaurs, which is just called the Chicxulub Impactor after the crater it created. When people talk about asteroid threats, Apophis is the name that comes up. That cultural awareness is actually important for planetary defense. Public support for asteroid detection and deflection programs is easier to maintain when people are aware of specific threats, even low probability ones. Apophis, with its memorable name and its dramatic 2029 flyby, keeps the issue in the public consciousness. So while the name might have been chosen partially as a pop culture reference, it's served a real function in making planetary defense a topic that people care about and understand. Section 14. What we're doing now. Let's talk about what's actually happening right now in terms of monitoring Apophis and preparing for various scenarios. Observation campaigns. Multiple telescopes around the world continue to track Apophis whenever it's visible. The asteroid isn't always observable. Sometimes it's too far away. Sometimes it's positioned where we can't see it from Earth. Sometimes it's too close to the sun in the sky. But during favorable viewing windows, astronomers take the opportunity to make precise measurements. These observations serve several purposes. They continually refine the orbital calculations, reducing uncertainty. They also monitor for any unexpected changes that might indicate something unusual happening with the asteroid, though such changes are highly unlikely. Radar observations. When Apophis passes close enough to Earth, radio telescopes like Goldstone in California can bounce radar signals off it. This provides incredibly precise distance and velocity measurements, much more accurate than optical observations alone. The last major radar observation campaign was in March 2021, when Apophis passed within 17 million kilometers of Earth. The radar data from that approach significantly improved our understanding of the asteroid's orbit and physical properties. The next optimal radar observation opportunity will be the 2029 flyby itself, when Apophis will be close enough for unprecedented radar mapping. Mission planning. Multiple space agencies are developing plans for possible missions to Apophis. These include reconnaissance missions, small spacecraft that would rendezvous with Apophis to study it up close, mapping its surface in detail, measuring its mass and density distribution, and characterizing its composition. This information would be crucial if we ever needed to deflect the asteroid. The 2029 Flyby Observation Mission. Plans for placing a spacecraft near Apophis during its 2029 Earth encounter to observe the effects of Earth's gravity on the asteroid in real time. This would provide valuable data for understanding gravitational interactions between asteroids and planets. Deflection demonstration concepts. Ideas for missions that would practice deflection techniques on Apophis, even though it's not on a collision course, treating it as a test target to validate our deflection methods. However, this is controversial. Deliberately altering Apophis's orbit could be seen as risky even if it's meant as a test. Software development. NASA and other space agencies are developing and refining software for calculating asteroid orbits, predicting impact probabilities, and planning deflection missions. Every close approach by an asteroid provides an opportunity to test and validate these systems. Public communication. There's ongoing work to develop better ways to communicate asteroid risk to the public. How do you explain a 1 in 100,000 probability in a way that's accurate but not alarmist? How do you keep people informed without causing panic? The 2029 Apophis flyby will be a major test of public communication strategies. The challenge will be explaining that the asteroid will pass very close, but won't hit us, while also acknowledging that the encounter will change Apophis's orbit in ways that could affect future impact probabilities. International coordination. Through organizations like the International Asteroid Warning Network, space agencies are working to improve coordination and information sharing. If a real threat emerges, having established relationships and communication channels will be critical. Technology development. The success of the DART mission in 2022 proved that kinetic impactors can work. Now researchers are studying the data from that mission to improve our models of how impacts affect asteroid trajectories. Work is also ongoing on other deflection methods: ion beam shepherds, laser ablation, enhanced gravity tractors. These technologies aren't ready for immediate deployment, but continued research means they'll be available if needed in the future. Policy development. Governments and international bodies are slowly working on the legal and policy frameworks for planetary defense. Who has the authority to launch a deflection mission? What are the liability rules if something goes wrong? How do we make decisions democratically when time is limited? These aren't glamorous topics, but they're essential. The technical challenge of deflecting an asteroid is solvable with enough time and resources. The political challenge of deciding to do it and organizing an international response is harder. Education and outreach. There's a significant effort to educate the next generation of astronomers, engineers, and planetary scientists about asteroid threats and planetary defense. University programs are incorporating planetary defense into their curricula. Public lectures and documentaries are raising awareness. The goal is to build a culture where planetary defense is taken seriously as an ongoing responsibility, not just a response to immediate threats. All of this work is happening even though Apophis probably won't hit Earth. And that's exactly the point. Planetary defense requires sustained effort over decades, not panic and rushed action when a threat is imminent. Apophis, whether it hits us or not, is serving as a focal point for building the infrastructure, technology, and institutions we'll need to defend Earth from future asteroid impacts. It's a dress rehearsal for the real thing. Section 15. The psychology of asteroid threats. Here's something that doesn't get enough attention. How do people psychologically process the idea that an asteroid might hit Earth? Asteroid impacts are a weird kind of threat. They're low probability, but high consequence, potentially catastrophic, but preventable with enough warning. Natural and impersonal, not caused by human action. Unavoidable individually, but addressable collectively. Distant in time, but certain eventually. This combination makes asteroid threats psychologically challenging to process. Let me explain why. The probability problem. Humans are notoriously bad at understanding low probabilities. A 1 in 100,000 chance feels like basically zero to most people, even though it's actually a meaningful risk when you're talking about global catastrophe. For comparison, your lifetime odds of dying in a car accident are about 1 in 100. Your odds of dying in a plane crash are about 1 in 11,000. So a 1 in 100,000 chance of asteroid impact is lower than these everyday risks, but not absurdly lower. Yet most people worry about car accidents, and some people worry about plane crashes, while almost nobody worries about asteroid impacts. This is partly because car and plane risks are more familiar and feel more under our control. The timescale problem. When something might happen in 2032, 2068, or even later, it's hard to feel urgency about it. That's far enough in the future that our brains don't treat it as a real, immediate concern. Climate change faces a similar psychological challenge. The worst effects are decades away, so it's hard to motivate action now, even though waiting makes the problem harder to solve. The agency problem. With most threats, individuals can take actions to reduce their personal risk. You can avoid smoking to reduce cancer risk. You can exercise to reduce heart disease risk. You can avoid high crime areas to reduce violence risk. But with asteroid impacts, there's nothing you as an individual can do. Either your government and the international community detect and deflect the asteroid, or they don't. Your survival depends entirely on collective action that's outside your control. This creates a sense of helplessness that many people find psychologically uncomfortable. It's easier to just not think about the threat than to dwell on something you can't personally influence. The fairness problem. There's something emotionally troubling about the randomness of asteroid impacts. Your risk doesn't depend on your choices or moral worth. It's just cosmic bad luck if an asteroid happens to hit your region. Humans have a psychological need to believe the world is fair, that good things happen to good people and bad things happen to those who deserve them. Asteroid impacts violate this belief completely. They're the ultimate example of random, morally neutral catastrophe. The denial mechanism. Faced with a threat that's low probability, far in the future, outside our control, and fundamentally unfair, many people simply choose not to think about it. Denial is a powerful psychological defense mechanism. This is why asteroid threats often get treated as science fiction or abstract speculation, even though they're scientifically well understood and historically documented. It's more comfortable to file them away as not real concerns than to grapple with the implications. The panic risk. On the flip side, some people overreact to asteroid news. When stories about Apophis or other near-Earth asteroids circulate online, you'll see comments predicting imminent doom, government conspiracies to hide the true danger, and fatalistic acceptance of inevitable destruction. This is the opposite problem from denial. It's treating a low-probability threat as a certainty. It often comes from misunderstanding the science or from general anxiety, finding a specific target to focus on. The communication challenge. For scientists and science communicators, the challenge is threading the needle between these extremes. You want to inform people accurately about the risk without causing panic. Convey that the probability is low without implying it's zero. Explain what's being done without promising complete safety. Motivate appropriate concern without inducing helpless fatalism. This is really hard. Get the tone slightly wrong and you either sound like you're fear-mongering or like you're dismissing a real risk. The silver lining. The good news is that Asteroid threats are one of the rare existential risks where we can see them coming with enough warning. We have the technology to prevent them. The solution is purely technical, not requiring difficult social or political changes. Unlike climate change, which requires massive behavioral and economic restructuring, or nuclear war, which requires complex geopolitical negotiation, asteroid deflection is straightforward. Find the rock, launch the mission, change its trajectory. Done. This makes asteroid threats psychologically easier to deal with for people who understand the science. It's a solvable problem. We're not helpless. We just need to invest in the detection and deflection infrastructure. The psychological challenge is getting people to care enough about a low probability future threat to support that investment now, while not caring so much that they panic unnecessarily. Apophis, with its dramatic 2029 flyby and its low but non-zero impact probability for future encounters, sits right in that sweet spot of being concerning enough to motivate action, but not so threatening as to cause panic. It's a teachable moment about asteroid risks in general, and it's a test of how well we can communicate about these threats to the public. Section 16. The bigger picture, planetary defense as a species. Let me zoom out and talk about what all of this means from a broader perspective, because asteroid defense is about more than just preventing one specific impact. For most of human history, we've been at the mercy of natural disasters. Earthquakes, hurricanes, floods, volcanic eruptions. These happened to us, and all we could do was react and try to survive. Asteroid defense is different. It's the first category of natural disaster that we can prevent entirely if we have enough warning and preparation. Think about what that means. For the first time in the history of life on Earth, one species has the technological capability to protect the entire planet from a category of cosmic threat that has caused mass extinctions in the past. That's profound. It represents a fundamental shift in our relationship with the natural world and with cosmic forces. It also represents a test of whether we can act collectively for the common good. Asteroid defense doesn't benefit any one nation or group. It protects everyone or no one. You can't build a wall to keep asteroids out of your country. You can't deflect an asteroid to make it hit somewhere else without risking it hitting somewhere worse. Either we cooperate as a species to detect and deflect threats, or we all remain vulnerable. In that sense, asteroid defense is a model for how we might need to approach other global challenges. Climate change, pandemic diseases, nuclear weapons. These are all problems that require international cooperation and long-term thinking. If we can build effective institutions for planetary defense, those same institutions and that same spirit of cooperation could be applied to other existential risks. Conversely, if we can't organize ourselves to handle something as straightforward as asteroid defense, where the threat is clear, the solution is technical, and the benefit is universal, what hope do we have for addressing more complex challenges? There's also something deeply meaningful about taking responsibility for Earth's protection. Our planet has existed for 4.6 billion years without any species actively defending it. Life has survived through luck and resilience, adapting to whatever catastrophes occurred. Now, for a brief moment in cosmic time, Earth has a species capable of conscious planetary defense. We're the planet's immune system against asteroid impacts, if we choose to be. That's a responsibility we didn't ask for, but it's one we have simply by virtue of having developed the necessary technology and understanding. With that capability comes a moral obligation to use it. Future generations, if we're successful in building a robust planetary defense system, will grow up in a world where asteroid impacts are no longer a meaningful threat, where they're a solved problem like smallpox or polio in regions with good vaccination programs. They might take it for granted, the way we take for granted that cities have fire departments and buildings have fire codes. But the absence of asteroid catastrophes in their future will be because we, right now, invested in detection and deflection. That's the bigger picture. Apophis is one asteroid. Whether it hits Earth in 2032 or 2068 or never, it's not the point. The point is building the systems and institutions to protect Earth from all asteroids, now and in the future. Every dollar spent on planetary defense, every telescope scanning the sky, every mission to test deflection technology, every international agreement on coordination and liability, all of these are investments in the long-term survival and flourishing of human civilization and all life on Earth. That's not hyperbole. That's just what's at stake. And the fact that we're having this conversation, that we're tracking Apophis and calculating probabilities and planning missions, shows that at least some people understand the stakes and are working to address them. The question is whether we'll invest enough, quickly enough, to be ready when the day comes that an asteroid threat is real and imminent. Apophis is giving us time to prepare. Let's hope we use it wisely. Section 17, Lessons from the Past. Before we wrap up, let's look at what happened the last time Earth faced a significant asteroid threat that people actually witnessed. Because history has lessons for us. The Tunguska event in 1908 is the most recent large-scale asteroid impact we have documented records of. An object estimated to be 60 to 190 meters across entered Earth's atmosphere over Siberia and exploded about 5 to 10 kilometers above the ground. The explosion was equivalent to 10 to 15 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. The blast wave flattened an estimated 80 million trees over 2,150 square kilometers. People and animals were knocked down over 60 kilometers away from ground zero. Windows shattered hundreds of kilometers away. If this had happened over a populated area, the death toll would have been catastrophic. But it happened over remote Siberian forest, so the human casualties were minimal, possibly zero, though records from that time and place are incomplete. Here's what's relevant to our discussion about Apophis. Nobody saw it coming. The first anyone knew about it was when it exploded. There was a bright fireball in the sky, then a massive explosion, then the blast wave, and the destruction. This was 1908. No satellites, no asteroid detection programs, no way to see it approaching. The asteroid came from the direction of the sun, which meant even if there had been telescopes watching, they probably wouldn't have spotted it. The aftermath is instructive. Scientists didn't reach the impact site until 1927, nearly 20 years after the event. The remote location, the political turmoil in Russia at the time, revolution, civil war, and the difficulty of accessing the area all delayed investigation. When scientists finally studied the site, they found no crater. This was puzzling until they realized the object had exploded in the air rather than hitting the ground. The lack of a crater initially led to all sorts of wild theories. Some people thought it was a comet rather than an asteroid. Others speculated about a black hole passing through Earth, or even an alien spacecraft crashing. It took decades of research to piece together what had actually happened, and even now, we don't know for certain whether it was an asteroid or a comet that caused the Tunguska event. The key lesson from Tunguska is this: without active detection and tracking, we're completely vulnerable to these events. We can't prepare, we can't evacuate, we can't deflect. We just get hit and deal with the consequences. The other lesson is that even a relatively small object, 60 to 190 meters, much smaller than Apophis, can cause massive destruction if it impacts or explodes over a populated area. Since Tunguska, we've had other reminders. The Chelyabinsk meteor in 2013 was much smaller, only about 20 meters across. But it still injured 1,500 people when it exploded over a Russian city. That's what a 20-meter object can do. Imagine what a 370-meter object like Apophis could do. These historical events demonstrate that asteroid impacts aren't theoretical risks or ancient history. They happen. They've happened in modern times. And they'll happen again. The difference now is that we have the capability to detect and track these objects before they hit us. Tunguska happened with no warning. Chelyabinsk happened with no warning. But if an Apophis-sized object were on a collision course with Earth today, we'd probably see it coming years or decades in advance. That advance warning is the difference between helpless catastrophe and preventable disaster. It's the difference between being victims of cosmic chance and being a species that can defend itself. Section 18, the Apophis Legacy. Regardless of whether Apophis ever hits Earth, it's already made an impact on planetary defense in important ways. It raised awareness. Before Apophis, most people didn't think about asteroid threats at all. Even after movies like Armageddon and Deep Impact in the late 1990s, asteroids were seen as Hollywood fiction, not real concerns. Apophis changed that. When the threat level was raised in 2004 and mainstream media started covering the story, millions of people learned for the first time that asteroid impacts are real, ongoing risks that we need to prepare for. That public awareness translates into political support for planetary defense funding, which translates into better detection networks and more research into deflection methods. It validated detection programs. The fact that we found Apophis at all, a 370-meter asteroid in an Earth-crossing orbit, proved that systematic sky surveys work. The asteroid was discovered as part of a NASA-funded program to catalog near-Earth objects. Without that program, we might not have discovered Apophis until it was much closer, giving us less time to study it and understand its orbit. The early detection meant we had years to refine our calculations and determine that 2029 wouldn't be an impact. It drove improvements in orbital calculation. The challenge of predicting Apophis's trajectory decades into the future, accounting for gravitational perturbations and the Yarkovsky effect, pushed astronomers to develop better modeling software and more sophisticated analysis techniques. These improved tools are now used for all near-Earth asteroids, making our predictions more accurate across the board. It motivated deflection research. The possibility that Apophis might need to be deflected helped justify missions like DART. When you're asking for billions of dollars to test asteroid deflection technology, it helps to have a specific example of why we might need that technology. Apophis served as the poster child for this is why we need to develop these capabilities. It highlighted gaps in our knowledge. The uncertainty about exactly where Apophis will pass during the 2029 encounter and how that will affect its future trajectory revealed how much we still don't know about asteroid dynamics. This has motivated more research into things like the Yarkovsky effect, asteroid rotation states, and how gravitational encounters alter orbits. We're learning from Apophis even without sending a spacecraft to it. It created a deadline. April 13th, 2029 is now burned into the consciousness of the planetary defense community. It's a date by which we want to have certain capabilities in place, certain questions answered, certain systems tested. Deadlines focus effort. The 2029 encounter has accelerated work that might otherwise have proceeded more slowly. It enabled planning for future missions. Space missions take years to plan and execute. The 2029 flyby gives mission planners a specific target date to work toward. Multiple proposals for missions to Apophis are in development, and the 2029 encounter is the anchor point for their timelines. Some missions would observe from Earth, others would rendezvous with Apophis before or during the encounter. Having this concrete event in the near future makes mission planning more tangible and urgent. In a very real sense, Apophis has been good for planetary defense, even though it's probably not going to hit us. It's been a wake-up call, a test case, a motivation for investment, and a focus for international cooperation. Future historians studying the development of planetary defense capabilities will likely identify Apophis as a turning point. The asteroid that made planetary defense a serious, funded, coordinated global effort rather than a niche research interest. Section 19. What you can do. Let me end with something practical. You might be thinking, okay, this is all interesting, but I'm not an astronomer or a rocket scientist. What can I, as an individual, actually do about asteroid threats? Here are some real, actionable things. Stay informed. Follow NASA's Planetary Defense Coordination Office, the ESA's planetary defense activities, and reputable science news sources. When stories about asteroids circulate, look for coverage from actual experts, not sensationalist headlines. Being an informed citizen helps combat misinformation and panic while supporting evidence-based policy. Support science education. Whether through volunteering, donations, or advocacy, supporting STEM education helps create the next generation of astronomers, engineers, and planetary scientists who will continue this work. Contact your representatives. Let your elected officials know that you support funding for NASA's planetary defense programs, the Vera Rubin Observatory, NEO Surveyor, and other asteroid detection and tracking initiatives. Political support matters. When lawmakers know their constituents care about an issue, they're more likely to fund it. Participate in citizen science. There are projects like Asteroid Zoo where volunteers can help analyze telescope images to identify asteroids. Your contributions actually help catalog near-Earth objects. Spread accurate information. When you see misinformation about asteroid threats on social media, politely correct it with accurate information from reputable sources. Help combat the spread of conspiracy theories and panic-mongering. Plan to watch the 2029 flyby. Mark your calendar for April 13th, 2029. If you're in the visibility zone, Europe, Africa, Western Asia, this will be a once-in-a-lifetime opportunity to see an asteroid pass close to Earth with your own eyes. Even if you're not in the visibility zone, the Chiao event will be covered extensively by media and live-streamed from multiple locations. It'll be a global moment of astronomical interest. Support space exploration more broadly. Many of the technologies needed for asteroid deflection, spacecraft, propulsion systems, remote sensing, benefit from general investment in space exploration. Supporting missions to Mars, sample return missions, commercial space development, all of this contributes to building the capabilities we'd need for planetary defense. Think long-term. In your own planning, whether personal or professional, factor in existential risks, including but not limited to asteroid impacts. This doesn't mean living in fear. It means recognizing that protecting civilization requires thinking beyond next quarter's profits or next election's results. Don't panic, but don't ignore it. The right attitude toward asteroid threats is calibrated concern. They're real risks that deserve attention and resources, but they're not imminent catastrophes that should dominate your daily thoughts. It's like fire safety. You should have smoke detectors and know where the fire exits are, but you shouldn't spend every moment worried about fire. The reality is that individual actions on asteroid defense are limited. This is fundamentally a collective challenge that requires government investment, international cooperation, and sustained scientific effort. But collective efforts are made up of individuals. Your vote, your voice, your education, your support, they all matter. Planetary defense will only be as strong as the political will and public support behind it. Apophis, whether it threatens us or not, is an opportunity to think about these issues and to support the work being done to protect Earth from cosmic hazards. If you made it this far, thank you for exploring this topic with me. Asteroid threats are one of those subjects that sit at the intersection of science, policy, international relations, and existential risk. They're complex, they're important, and they're surprisingly underappreciated by the general public. Drop a comment and let me know. Do you think we're doing enough to prepare for asteroid threats? Should we be spending more on planetary defense? And are you going to watch the 2029 Apophis flyby? Because if you are, mark your calendar, April 13th, 2029. It's going to be historic. I'll see you in the next video, and hopefully, I'll see you in a world that never gets hit by Apophis or any other asteroid. Stay safe out there, and keep watching the skies. If you made it this far, thank you for exploring this topic with me. Asteroid threats are one of those subjects that sit at the intersection of science, policy, international relations, and existential risk. They're complex, they're important, and they're surprisingly underappreciated by the general public. Drop a comment and let me know. Do you think we're doing enough to prepare for asteroid threats? Should we be spending more on planetary defense? And are you going to watch the 2029 Apophis flyby? Because if you are, mark your calendar, April 13th, 2029. It's going to be historic. I'll see you in the next video. And hopefully, I'll see you in a world that never gets hit by Apophis or any other asteroid. Stay safe out there, and keep watching the skies. Conclusion. So here's where we are with Apophis. We discovered it in 2004. Initial calculations were terrifying. A real possibility of impact in 2029. Further observations ruled that out. The asteroid will pass very close on April 13th, 2029. Close enough to see with the naked eye, but it won't hit us. However, that close passage will change Apophis's orbit in ways we can't predict precisely until we observe the encounter. There's a possibility, small but real, that Earth's gravity will bend the trajectory just right to send Apophis back on a collision course with us in a future encounter. The year 2032 has been mentioned in some research papers as a potential impact date, though current official NASA assessments don't list it as a significant concern. The year 2068 is the more commonly discussed potential impact date, though the probability there is also very low, less than 1 in 100,000. The truth is, we won't know for certain whether Apophis poses a real threat to Earth until after the 2029 flyby. The close encounter will give us the detailed observations we need to calculate the future orbit with much better precision. Most likely, overwhelmingly likely, those calculations will show that Apophis misses Earth completely on all future approaches. The probabilities will drop to effectively zero, and Apophis will transition from being a potential threat to just being a scientifically interesting object. But there's a chance, however small, that the 2029 encounter reveals a real impact threat for 2032, 2036, 2068, or some other future date. And if that happens, we'll have to decide what to do about it. The good news is that we have options. Kinetic impactors, gravity tractors, nuclear devices. We have multiple methods for deflecting asteroids, and the DART mission proved that at least one of them works. With enough warning time, we could almost certainly prevent an impact. The challenge would be organizing the international response, deciding who acts, and executing the mission flawlessly under enormous pressure and public scrutiny. What Apophis really represents is a test of our detection capabilities, our tracking precision, our deflection technology, our international cooperation, and our ability to think long-term about planetary protection. Even if Apophis never threatens us, it's serving a valuable purpose. It's keeping planetary defense in the public consciousness. It's motivating continued investment in asteroid detection and tracking. It's forcing us to develop the technologies and institutions we'll need to defend Earth from future impacts, because Apophis won't be the last asteroid to threaten Earth. Asteroid impacts are not a question of if, but when. On long enough timescales, a catastrophic impact is statistically certain. The question is whether we'll be ready, whether we'll have invested in the detection networks to find threatening asteroids early enough, whether we'll have tested deflection technologies sufficiently to be confident they'll work when we need them, whether we'll have built the international frameworks to coordinate a response. April 13th, 2029 is coming. In less than 5 years, humanity will watch an asteroid the size of the Eiffel Tower pass closer to Earth than our communications satellites. It will be a spectacular historic event, the closest approach of an asteroid this large in recorded history. And then we wait. We watch where Apophis goes. We calculate its new orbit. And we find out if this cosmic visitor is just passing through, or if it's coming back. Most likely, we'll breathe a sigh of relief and move on with our lives. But just maybe, we'll find out that we have a decade or a few decades to prepare for an impact. Either way, Apophis has already given us something valuable. A deadline to take planetary defense seriously, a test of our capabilities, and a reminder that we live in a universe where catastrophe can arrive from space with no warning if we're not watching.